Right. Uh, One of you tell me, what is the difference between conductors and insulators? Basic difference between conductors and insulators.
The conductors allows the current to flow through it and insulators doesn't.
Okay. Like, which property of conductors or how are conductors able to allow current to pass through them? Like, what is, I mean, in terms of electron structure, what is different between conductors and insulators? Okay.
Because conductors have more free electrons.
They have free electrons. Insulators do not have free electrons. Fine. Now, what are free electrons? See, in an atom, we know electrons revolve around the nucleus. Let's consider an electron revolving in this orbit around this nucleus. Okay. Nucleus is positively charged. It has a charge of plus Ze. Electron has a charge of minus E. Fine. Now, in the chapter atoms, we derived an expression for total energy of electron in an orbit also. In case it is hydrogen atom, it is minus 13.6 into, I think, Z divided by N square. Or, okay, Z square by N square, right? So as the orbit number increases, the total energy of electron increases. So greater the distance of electron from the nucleus, greater is its total energy. Fine. Now suppose there are multiple orbits and multiple electrons. Fine. And you know there are something called shells in atoms. Okay, shells in which electrons are distributed. The first shell can accommodate 2 electrons. Next shell can accommodate 8 electrons. The third shell can accommodate 18 electrons and so on. Okay. You must have studied in chemistry. So basically, electrons in the last shell will be the most distant from the nucleus. So electrons in the last shell are the most energetic electrons. Fine. The last shell, what is it called? Okay. As far as I know, it's called the valence shell. Okay. Electrons in the valence shell are the most energetic electrons and they are the farthest from the nucleus. So they are the most loosely bound electrons in an atom. Okay. How many ever are there? Let them be. They are the most loosely bound electrons in an atom, right? Now, if it's just one atom, those electrons also will be bound to this nucleus. They'll have to revolve around this nucleus only. But when atoms combine to form a molecule, okay, when they like basically what happens in a chemical bond, two nuclei come close enough or two atoms come close enough, okay, such that their electron clouds overlap. Okay, and when electron clouds overlap, what can happen is the electron from one atom, okay, can sometimes go around the other atom as well. They'll be going around like this. The electron orbits and all will get disturbed when bond forms. Fine. That is what happens in bonds, chemical bonds. Electrons will revolve around multiple nuclei, not just one nucleus. Now, how free an electron is to roam around another other nuclei or to roam around in the entire material depends on how much energy it has. Okay. Greater the energy of electrons, lesser it will be bound to the particular nucleus. Right. So in every material, okay, I'm not talking about a single atom, I'm talking about a material. Material is a combination of atoms, right? In every material, there are certain energy levels which the valence electrons can have. Okay, that is called the valence band. See, in Bohr's model of the atom, electron in a specific orbit has a specific amount of energy. But in Bohr's model, we consider a single electron species. Other electrons are not there. But if there are multiple electrons in an atom like this, okay, like you imagine these electrons revolving around the nucleus in 3 dimensions, you imagine them revolving. Sometimes electrons will be close to each other, sometimes they'll be far from each other. Okay. So As electrons move closer and farther from each other, the electrostatic repulsion between them will cause the energy of an electron to change. Okay. When there are multiple electrons in an atom, the total energy of electron not only depends on its interaction with the nucleus, it also depends on its interaction with the other electrons. Fine. And electrons are moving around, no? Randomly they'll be moving around. So the total energy of any particular electron cannot be fixed. It'll keep varying. So the first orbit or the first shell that exists, all the electrons in the first shell won't have one amount of energy. They'll have a range of energies. Okay. Similarly, the last shell that exists, all the electrons in the last shell won't have a fixed amount of energy. They'll have a range of energies. That range of energies is called valence band. Fine. The range of energies for which an electron is still bound to the nucleus. Okay. That last band or range of energies is what you call as valence band. Fine. Now, if you supply some more energy to those valence electrons, they will become free from the nucleus. They'll be free to roam around in the entire material. Okay. Then they are said to be in the conduction band. So electrons in the valence band have sufficient energy only to stay with one nucleus or maybe two nuclei participating in bond. Okay. But electrons in the conduction band have sufficient energy to roam around in the entire material. So there is an energy difference between valence band and conduction band. Now you assume, consider something like this. Let's say these are the energy levels of electrons in the valence band. This is the lowest energy with which an electron can be in the valence band. And this is the highest energy with which an electron can be in the valence band. Okay. Now, depending on the kind of interactions that the electron is going on, some electrons will be close to the lower side of the valence band energy. Some electrons will have energy close to upper range of valence band energy. Fine. But these electrons are bound to revolve around one or two nuclei. They cannot go around in the entire material. Now, if you give sufficiently high amounts of energy, then the electron will become free to roam around in the entire material. Then those energy ranges or those levels of energy are called conduction band. You can visualize energies in the conduction band like this. Basically, the thickness of the color represents the energy here. So valence band energies will be lower, conduction band energies will be higher. Okay. For conduction band also, there is a lower, there is a minimum and a maximum. So electron needs to have at least this much amount of energy to be free to roam around in the entire material. And you give more and more energy, it will be relatively more free to roam around. But if you give too much energy to the electron, what will happen? It will leave the metal as altogether. Okay, electron emission will happen. So there is an upper limit also for the conduction band. Right. Now, in insulators, what happens? There is a significant energy difference between the valence band and the conduction band. Okay. So there is a significant gap between the highest energy level of the valence band and the lowest energy level of the conduction band. That gap is more than or equal to 5 electron volts. So electrons will typically be in the valence band, right? So by themselves or by interacting with other electrons, they will never be able to attain sufficient energy to jump into the conduction band. Okay. and there can never be electrons between a conduction band and valence band. Okay, this is called the forbidden energy level. There can be no electrons which have energies in this range between the maximum of the valence band and the least of the conduction band. Those energy levels are banned. Okay, not possible. So that is called forbidden energy levels or forbidden energy gap. Fine. So in insulators, electrons won't have enough energy to jump into the conduction band. Fine. What you see on the lower side is valence band, upper side is conduction band. Okay. In conductors, it so happens that the energy required to roam around the entire material is almost equal to the highest energy in the valence band. So in case of conductors, the situation will be like this. Suppose this is the valence band. Okay, valence band has a certain minimum and a certain maximum amount of energy. So electrons having this range of energies can roam around one or two nuclei. Okay, they can participate in bonds basically. That is what I mean. But it so happens that in case of conductors, the conduction band kind of overlaps with the valence band. So it's like this. This is the conduction band. So high energy electrons in the valence band also belong to the conduction band. Means these electrons, particularly this one and this one, they can participate in bonds. They can also roam around in the entire material. These are what we call as free electrons. So there is almost no gap, or in fact, there will be an overlap between the conduction band and the valence band in case of conductors. That is why there are a lot of free electrons in the in conductors. Okay, if you consider copper, copper has one electron in its last orbit. That one electron which is in its last orbit is both a valence electron as well as a conduction electron. Fine. So every copper atom contributes one conduction electron. And how many ever copper atoms are there, those many conduction electrons will be there. That is why copper is a very good conductor. Okay. So in conductors, the energy gap is zero. Fine. In insulators, the energy gap is greater than 5 electron volts. That's a large energy gap which electrons won't be able to cross on their own. But we discussed this point also when we talked about dielectrics. Dielectrics are basically insulators. If you apply a very strong potential difference across a dielectric, the insulator can turn into a conductor. Okay, if you apply a very strong potential difference, what happens is these electrons will gain sufficient energy to jump into the conduction band. Okay, that is how lightning takes place, dielectric breakdown takes place. We had discussed all that. Okay. Now, in case of semiconductors, okay, that is what is the topic for, topic of this chapter. In case of semiconductors, the energy gap between the conduction band and the valence band is small. There is a gap, but it's a small gap. Okay. The highest energy level of the valence band and the lowest energy level of the conduction band, they have a very small difference between them or small energy gap between them. And that energy gap is approximately 3 electron volts. Okay. Not the same for all semiconductors, but on average, it is around 3 electron volts. And 3 electron volts is a sufficiently small enough energy that some valence electrons can attain and jump into the conduction band. Not all of them, but some of them can occasionally gain that energy and jump into the conduction band. Okay. So in semiconductors, not all valence electrons, but randomly some valence electrons will be present in the conduction band. They'll be free to roam around in the entire material. Okay. But it's not like conductors. In conductors, every atom contributes conduction electrons. In semiconductors, every atom cannot do that. Okay, randomly a few atoms or electrons of a few atoms somehow gain that energy due to collisions or whatever and jump into the conduction band. Okay. And this mechanism is very important. When an electron jumps from valence band to conduction band, okay. So suppose an electron has gone from valence band to conduction band. Basically, what happens is it leaves a vacancy. Okay. We call that as a hole. If an electron jumps from valence band to conduction band, now in conduction band, it is free to roam around, no? In valence band, it is bound to be around the nucleus. You can visualize it like this. Suppose this is the nucleus. Okay. And one range of energies we will call as valence band. I am intentionally drawing it thick. So this is the lowest energy of the valence band. This is the highest energy of the valence band. And another range of energies we will take as conduction band. Fine. Conduction band, I will stretch it like this because in conduction band, it is free to roam around in the entire material. It won't be bound to one nucleus. Okay. So think of it like this. Now, as long as it is in the valence band, it will be around that nucleus itself, or maybe two nuclei participating in a bond. Once an electron, okay, jumps from the valence band into the conduction band, basically understand what happens. You look at this region, look at this atom. Atoms are electrically neutral. How many ever protons are there, those many electrons will be there. So this region as such is neutral. Okay. But if one of these electrons jumps off into the conduction band, okay, by leaving a gap here, let's say the electron goes to the conduction band. When it is in the conduction band, it is free to roam around. So it won't stay around that nucleus anymore. It has gone away from that place. Now, earlier, that space was neutral. Atom was neutral. But when an electron goes away, then what will happen? Electron is negative charge is gone away. Then there will be a net positive charge in this region, and negative charge will be roaming around. So we say that it leaves behind a hole. Okay, and this electron is a conduction electron. So whenever a valence electron jumps into the conduction band, it most likely goes away from that place. Then that place will be left behind with a net positive charge. Okay. When the electron was in the valence band, it was neutral. That space was neutral. But when electron leaves from that space, the space becomes positively charged. We say it's a hole. Basically, it is a region which is ready to accept an electron. Okay. Without that electron, the atom is missing something or the bond will be missing something. Okay. So that space is ready to accept an electron. So we call it as a hole. So understand this concept. When valence band electrons jump into conduction band, they leave behind holes. Hole is not a particle. Hole is basically a space which has a net positive charge, which is ready to accept an electron. Okay. Electron is a particle. It actually takes negative charge with it. Hole, as I said, it's a space which is ready to accept an electron. We say hole is positively charged. That is correct. The space is positively charged, but hole is not a particle. Okay. So basically, this is what happens in semiconductors. Randomly, in some atoms, the electrons jump into the conduction band. The valence electrons jump into conduction band, creating an electron. Assume these are the valence electrons, the yellow ones. When an electron jumps into the conduction band, it creates an electron hole pair. How many ever conduction electrons are there, those many holes will be there. Okay. Such semiconductors are called intrinsic semiconductors or elemental semiconductors. Fine. The best example is silicon. Now, silicon, what is a valence? What is that number called? Valence number. Okay, how many electrons does silicon have in the last shell? Valency. What is the valency of silicon?
Sir, 4.
Four. Okay. So basically, silicon forms four bonds. Okay, each atom of silicon forms four bonds with its surrounding atoms. So this is how the silicon lattice structure looks. If you consider one silicon atom, you can see that it is bonded to four other atoms, covalent bonds. Now, what happens in a covalent bond? Each participating atom contributes one electron to it. So each bond here has two electrons. Fine. So in 3D, this is what it looks like, the silicon lattice structure. But if you visualize it in 2D for our convenience, okay, you can think of it like this. So each silicon atom contributes one electron to the bond that it forms with another silicon atom. So you can see that this silicon-silicon bond has two electrons, one from one silicon, the other from the other one. Okay. Now, these bonds are all formed by valence electrons, that last shell electrons. Now, as I was saying, some of these valence electrons may sometimes gain sufficient energy to jump into the conduction band. Okay. So what happens when a valence electron jumps into a conduction band? That bond between the two silicon atoms will be missing something. Okay. That region of space in the material will be left behind with a positive charge, and the electron will be roaming around. It'll become a free electron. Okay. The electron has jumped off from here or jumped out from here. It becomes a free electron. So this can happen randomly anywhere in the material. So you can imagine some more electron hole pairs. So if an electron jumps out from a bond, it leaves behind a hole, basically a vacancy. So in intrinsic semiconductors, this is what happens. Basically, they are semiconductors on their own. What are semiconductors? They have very few conduction electrons. Okay. Such materials are called semiconductors. Okay. So in intrinsic semiconductors, what happens is number of conduction electrons will be equal to number of holes. Now in this chapter, we just use the term electrons, but we refer to conduction electrons. So in intrinsic semiconductors, number of electrons will be equal to number of holes. Okay, or let us be more precise only. Number of conduction electrons will be equal to number of holes. There will be a lot of other electrons also, which are in the valence band and further inside the valence band also. In further lower energy levels also, lot of electrons will be there. Okay, few electrons will be there in the conduction band. That number, the number of conduction electrons will be equal to number of holes. Now, if the total number is equal, then the number of electrons per unit volume, okay, capital N refers to number, actual number, okay, small n refers to number per unit volume. We call it as number density. So small n is capital N divided by volume. Fine. Now, in a certain volume of silicon, the number of conduction electrons is equal to number of holes. And if number of conduction electrons is equal to number of holes, the concentration of conduction electrons will be equal to the concentration of holes. Okay, this is what happens in an intrinsic semiconductor. Fine. And because the, the number of conduction electrons is actually very small, the conductivity will not be that high. That is why they are called semiconductors. The name itself is self-explanatory. Okay, had it been carbon, every atom of carbon would have contributed a conduction electron. But you see in silicon, not every atom does that. Randomly, a few atoms will do that. Okay, so there will be a very small concentration of conduction electrons, so it won't be so good a conductor. So intrinsic semiconductors as such are not good conductors at all. Fine. So basically in intrinsic semiconductors, hole concentration will be equal to conduction electron concentration. Now see, these conduction electrons are free to move around. So they are called charge carriers. Conduction electrons are charge carriers. Obviously, they are negative charge carriers. Okay. What about holes? Now, hole is just a vacancy that has been created. It's not a particle, as I said. So that bond is lacking something there. Now, a hole also, see these circles that you see in this diagram represent electrons. Fine. Valence electrons. The yellow ones are the conduction electrons. They have somehow attained extra energy and jumped out. Valence electrons are not stationary. They'll be revolving around the nucleus, right? So consider one of these valence electrons. Let's say this one. This valence electron revolves around, okay, here it is shown to be part of this bond. So it revolves around these two nuclei, silicon nuclei. But who is going to tell the electron to revolve only around these two nuclei? When it comes here, when it comes close to this silicon, it may occasionally go around this one as well. Okay. So basically, this valence electron, the one that I have star marked, can shift to this place. Fine. It can fill the hole. And when it does that, it did not become a conduction electron. It just jumped from one bond to another bond. It didn't become free. It's still in the bond itself. Okay. It's not completely free. So its energy will be valence energy itself. It just goes from one bond to another. When it does that, the hole will shift to this place. Okay. When the conduction electron goes to that, not conduction, sorry. When the valence electron goes into a hole, automatically another hole will get created here. So holes can also shift, but holes don't shift on their own. How do holes shift? Electrons from the surrounding bonds should take this place, should fill a hole, then another hole will get created in that bond. That is how holes can also shift. And holes are also considered charge carriers. And obviously they are positive charge carriers. So remember, conduction electrons move on their own. Holes do not move on their own. Electrons from the surrounding bonds will have to fill these holes. Then it's like the hole shifts to that bond, to the next bond, and so on. So holes can shift. Conduction electrons can anyway shift. They will be roaming around. So both are called charge carriers. Now think and answer, which of these, conduction electrons or holes, which one has greater mobility? Mobility means free to move. Okay. Conduction electrons and holes are both charge carriers, but which of them is relatively more free to move? Electrons or holes? Or do you think they have the same amount of freedom to move around? And it's obvious, no, conduction electron can move on its own. Okay, they will be moving around. Hole cannot move on its own. A surrounding electron has to come and take its place, then only hole will shift. Okay, so which is free to move? Conduction electrons are more free to move. Okay, therefore, mobility of conduction electrons is greater than the mobility of holes. Okay, mobility is a well-defined term. We had talked about this in current electricity way back. Mobility, denoted by the symbol mu, is basically the drift velocity per unit electric field. You know that to make electrons drift, you need to apply an electric field. Okay, and there's a proper formula for drift velocity also. E by m, force by mass is acceleration into relaxation time. Okay, this is the drift velocity. So drift velocity per unit electric field is what we call as mobility of electrons. There in current electricity, we only talked about conduction electrons. So this is electron mobility. Right? In semiconductors, along with electrons, holes are also charge carriers. So electrons have a certain amount of mobility. Holes have a certain amount of mobility, but electrons have more mobility compared to holes. Okay. Because electron is free to move on its own. Hole is not a particle to move around. It's a space which is lacking electrons. So if surrounding electrons come and take this space, then the hole can shift. Okay. So these terms are important. Charge carriers, mobility, concentration of charge carriers. So in intrinsic semiconductors, how many ever electrons jump out of bonds, those many holes will be formed. So concentration of conduction electrons will be equal to concentration of holes. Now, sometimes in questions, they just say concentration of electrons, concentration of holes. They are referring to conduction electrons only. Okay, fine. But we know that as such, intrinsic semiconductors don't have a good conductivity. Now, the actual use of semiconductors or actual application of semiconductors is when you can is or semiconductors are interesting materials because you can adjust their conductivity. Right? How to adjust conductivity? You should increase the charge carrier concentration. You can increase conduction electron concentration, or you can increase hole concentration. Okay. How is that done? That is done by a process called doping. Okay. Can any of you tell me what is doping of a semiconductor? Fine. Basically, doping means adding impurities. Impurities means what? Adding atoms from other elements into an intrinsic semiconductor. Consider silicon itself. Silicon valency is 4. Okay, so it tends to form 4 bonds with the surrounding silicon atoms. Now, atoms which are similar in size to silicon can be used to replace these silicon atoms. Okay, what are the atoms which are similar in size to silicon? Atomic number 13, aluminium, and atomic number 15, phosphorus. Consider these two. Aluminium has 3 valence electrons, phosphorus has 5 valence electrons. Okay. Imagine replacing one of these silicon atoms with aluminium. Okay. Aluminium atom, silicon atom have almost the same size. So if you replace one of these silicon atoms with aluminium, aluminium has only 3 valence electrons, so it can bond with 3 surrounding silicon atoms. Okay, you can see the 3 bonds here, 1, 2, 3. The fourth bond on the other side, silicon has contributed its electron, but aluminum does not have an electron to contribute. So that bond is lacking something. Okay, so automatically a hole is created. A vacancy is created for an electron. But understand this process carefully. What we did here is we removed a silicon atom. Atoms are electrically neutral. Okay, so when you remove silicon, what you are doing is you are removing 14 protons and 14 electrons with it. Okay, silicon atomic number is 14, no? So 14 protons, 14 electrons are removed. And then you imagine adding aluminium atom. When you add aluminium, you are adding 13 protons and 13 electrons. So what you removed is neutral. What you added is also neutral. So you are not giving any net charge to the semiconductor. Net charge is still 0. But when silicon is replaced with aluminium, you will automatically see some vacancies. You will automatically see some holes. Okay. Now aluminum valency is 3. So basically what we have done is we have doped silicon with a trivalent impurity. Okay. And when you dope silicon with a trivalent impurity, you will be creating holes. Now along with these holes, the existing electron hole pairs will anyway be there. In that silicon lattice structure, whatever is there, some electrons would have jumped out of their bonds, no? Okay. Those occasional conduction electrons will anyway be there. In addition, you have these new holes now, new vacancies. Now see, you have created new holes doesn't mean you have given positive charge. Fine. There is one proton missing in the nucleus of aluminum compared to silicon. One proton is missing, one electron is missing. Okay. Protons don't form bonds. No, they don't participate in bonds. So lack of proton does not create a lack of anything here, but a lack of electron in the aluminum creates a lack in the bond, creates a deficiency in that bond. It creates a hole. So when you dope silicon with a trivalent impurity, what happens is the concentration of holes will be greater than the concentration of electrons. Okay, there will still be conduction electrons, holes. These electron hole pairs will anyway be there. In addition, you will have extra holes. Okay, in the material. So concentration of holes is more than concentration of electrons. And holes are positive charge carriers, electrons are negative charge carriers. So basically this means positive charge carriers are dominating. And if positive charge carriers dominate, we call it as a p-type semiconductor. So if you dope silicon with a trivalent impurity, you get a p-type semiconductor. Fine. It's important to understand what happens. Silicon naturally has electron hole pairs. So this whole electron pairs will anyway be there. Fine. But if you replace some of the silicon atoms with aluminum, basically what you'll be doing is you'll be creating extra holes. Fine. In addition to the electron hole pairs which already exist, you'll be creating extra holes. So as a result, the total concentration of holes will be greater than the concentration of free electrons. And since holes are positive charge carriers, we call such doped semiconductors. Okay. Silicon doped with trivalent impurity. This semiconductor is now called a p-type semiconductor. Okay. Now, what is the uh, purpose of doping? What is the intention behind doping? You have more charge carriers now. Already existing whole electron pairs are there. In addition, you have some more holes, which are also charge carriers. Means you have increased the charge carrier concentration. If you are increasing charge carrier concentration, you are increasing the conductivity of the material. Okay. And conductivity will be proportional to level of doping. Okay, you introduce more and more aluminum atoms, you'll be creating more and more vacancies in the bonds, more and more holes. So you are increasing the charge carrier concentration. Okay. Now, usually in doped semiconductors, okay, there's another type of doping also we'll discuss. Usually in doped semiconductors, these, like you can see here, we have introduced aluminum. As a result, one extra hole has been produced. So usually when you dope semiconductors, what happens is these new charge carriers that are produced, their number will dominate the existing number of charge carriers. Okay. As such in semiconductors, the charge carrier concentration is very low. So when you dope it, okay, usually what happens is these new charge carriers that are formed, their concentration will dominate the existing charge carrier concentration. Fine. So in a p-type semiconductor, the number of holes or the concentration of holes will be way greater than the concentration of electrons. Okay. But what is the net charge on a p-type semiconductor? It's still zero. P-type has more holes than electrons, but the net charge is still zero because, as I said, a neutral atom silicon is removed, a neutral atom aluminum is introduced. So you removed 14 protons, 14 electrons, you introduced 13 protons, 13 electrons, right? So there is a lack of one electron. That lack is what appears as a hole. One proton is also missing. Okay, so as such, the net charge on a p-type semiconductor is zero itself. Fine. Next, if you dope silicon with phosphorus, phosphorus the valency is 5. So suppose a silicon atom from here is replaced with phosphorus. Phosphorus valency is 5, so it brings with it an additional valence electron. Now, 4 of its valence electrons will form bonds with 4 silicon atoms that are surrounding it. But this fifth valence electron will be free. It doesn't have a place to sit. That means it becomes a free electron. Okay. So the fifth valence electron of phosphorus becomes a free electron. Now, in addition to that, the existing electron hole pairs will anyway be there. Okay. Some electrons jump out from their bonds in silicon. So the existing electron hole pairs will be there. In addition, you will have new or extra conduction electrons. So phosphorus, the valency being 5, we call it as a pentavalent impurity. So if you dope silicon with a pentavalent impurity, concentration of conduction electrons will be much higher than concentration of holes. And because electrons are negatively charged, we call this as an N-type semiconductor. Okay. So again, understand what happens. We removed one neutral silicon atom, we introduced a neutral phosphorus atom. So we are not adding any net charge. We are giving 15 protons, 15 electrons this time. The 15 protons will stay inside the nucleus. Out of the 15 electrons, one electron will be free to roam around. So that is how we have increased its conductivity now. Right? So there are two types of doped semiconductors, p-type semiconductor and n-type semiconductor. If you dope with pentavalent impurity, you get an n-type semiconductor. Pentavalent means you are introducing extra electrons. Electrons negatively charged, so n-type. If you dope with trivalent impurity, trivalent means one electron is lacking, means one hole is produced. Hole is positively charged, so we call it p-type semiconductor. Okay. Both p-type and n-type semiconductors, basically doped semiconductors, are called extrinsic semiconductors. Why do we do doping? Because we want to adjust the conductivity of the material, and you can adjust its conductivity depending on the level of doping. More doping will give rise to more conductivity, less doping, less conductivity. Okay, fine. We'll stop it here for today.